So now we have a table, we have a cube, we have a camera and a robot arm in our scene. We will see now how we can prepare the scene for data collection with the perception package. So here is our URDF file that we used to import our robot. So we used URDF importer from Unity, and we also imported the perception package. Now how we can use domain randomization in order to train our model with specific data that has to do with RGB image and pose. And finally, we will create by training our object pose estimation model. So here it is important to know that the first thing, it is a Unity package. The second thing it is specific algorithms that have to do with data storage, and finally we have Python code in order to develop our final algorithm. So let's go on with the Unity. Here is our project. Here we have the robot. So first of all, let's equip the camera for data collection. So the images you generate to train your deep learning model and the images you later use for inference during the pick and place task will need to have the same resolution. So first of all, we need to set this resolution. So go to the game view right here, click on the drop down menu in front of display 1, then click on the drop down menu in front of display 1, then click plus to create a new preset and make sure type is set to fixed resolution right here. Set width to 650 and height to 400 and click OK. So here is the new resolution that we will use. Now we need to add a few components to our camera in order to equip it for synthetic data generation. So we will select the main camera right here, the main camera game object in the hierarchy tab always, and then we will go to the inspector tab and click add component. So start typing perception camera, here we are, and then we will click on this script to add it as a component. Our camera is now a perception camera. From the top menu bar of the editor, go to Edit Project Settings, then go to Editor, right here, and uncheck Asynchronous Shader Compilation. So go down, here we are, Asynchronous Shader Compilation. It is under the shader compilation settings. And now you can close this window. And in the inspector view for the main camera component, you can see an empty list. List is empty right here. This is the list of labelers. So for each type of ground truth you wish to generate alongside your capture frames, you will need to add a corresponding labeler to this list. So in our project, we want to extract the position and the orientation of an object. So we will use the bounding box 3D labeler. So here we are in this inspector view of the perception camera component. Click on this plus button and select bounding box 3D labeler. This labeler will annotate the captured output with 3D bounding boxes of game objects in the scene that are actually labeled If the perception camera show labeler visualization option is enabled, this means that these bounding boxes will also be visualized in real time in the scene view as data is generated. So once you add the labeler, then the inspector view of the perception camera should look like this. Now, what we have already done is actually preparing our model to collect RGB images from the camera and associated 3D bounding boxes for objects in our scene. We still need to specify which objects we would like to collect poses for using the labeler. Right here we just added. So now we will only collect the pose of the cube, but you can add more objects if you would like. So you will notice that the bounding box 3D labeler has a field named ID label config. The label configuration we link here will determine which object's poses get saved in our dataset. So in the project tab, right click right here, the assets folder, and then click create, then go to perception and click ID label config. This will create a new asset file that is named ID label config. It is inside the assets folder. Here it is. So this type of label configuration includes a list of labels. Each label has a unique numerical ID. So by assigning this configuration to a labeler, we tell the labeler to only capture objects that carry labels that are included in our configurations list of labels and ignore all the others. So we will assign this configuration the bounding box 3D labeler we just added to the perception camera component. So select the main camera object from the hierarchy tab, and in the inspector tab assign the newly created ID label config asset to the ID label config field. To do so, you can either drag and drop this one into the corresponding field of the labeler right here, or click on this circular button, which will bring this one, and you can also click ID label config. So the perception camera will look like this right now, but we need to assign a label to the cube object and add the same label to this ID label config, since it is the pose of the cube that we wish to collect. So we will select the cube right here, and in the inspector tab, click on the add component button. We will start typing labeling. So here we are. And then in the UI, you will see that there is this labeling, the added labels, and click to add new label button and change the new label to cube. Delete this one, cube position. Then click to add to label config, and below other label configs in project, right here, there should be ID label config. Click on add label and then close the window. Now the cube position label is added to both the cube object and the ID label config label configuration. So here we have the cube position, here we have the ID label config, and based on asset name, we have the cube right here. Now we will see what is domain randomization. Domain randomization is a simple technique for training models on simulated images that transfer to real images by randomizing rendering in the simulator. So performing robotic learning in a physics simulator could accelerate the impact of machine learning on robotics by allowing faster, more scalable, and lower cost data collection that is possible with physical robots. But the purpose of domain randomization is to provide enough simulated variability at training time such that when we test the model, we can generalize to real world data. So we randomize the aspects of the domain for each sample used during training. For example, number and shape of objects, position and texture of all objects, textures of the table, position, orientation, number of lights in the scene, type and amount of random noise added to images, and things like that. Now let's go on with Unity, and now we will be collecting training data from a simulation. Actually, most real perception use cases occur, of course, in the real world. So to train a model to be robust enough to generalize to the real domain, we rely on this technique that is called domain randomization. So instead of training a model in a single fixed environment, we randomize aspects of the environment during training in order to introduce sufficient variation into the generated data. So this forces the machine learning model to handle many small visual variations, making it actually more robust. So we will randomize the position and the orientation of the cube on the table, and also the color, the intensity, the position of the light. So note that the randomizers in the perception package can be extended to many other aspects of the environment as well. Now, to start randomizing our simulation, we will first need to add a scenario to our scene. So scenarios control the execution flow of our simulation by coordinating all randomizer components that are added to them. So let's go to the hierarchy window, click the plus button and select create empty. We will rename the newly created game object to simulation scenario. So write simulation scenario. Select this game object, and in the Inspector tab, click on the Add Component button. Start typing, pause, estimation scenario. Here we are. Ensure that the automatic iteration is also checked, is enabled. So each scenario executes a number of iterations, and each iteration carries on for a number of frames. These are timing elements you can leverage in order to customize your scenarios and the timing of your randomizations. So the randomization workflow involves two types of C# classes: randomizers and randomizer tags. Randomizers are added to the scenario and perform the actual randomization tasks, while randomizer tags are attached to objects in the scene so that randomizers know which objects to target. One randomizer can target many different randomizer tags. Now we will go back to the simulation scenario. We will return to the list of our randomizers. So go to simulate scenario, click add randomizer, and right here Y rotation randomizer. Here it is. Then go to the cube, and in the inspector tab, go back here, add component, and write Y rotation randomizer tag. So here we added the Y rotation randomizer tag component. Now we will run the simulation by clicking the play button and inspect how the cube now switches between different orientations. Here it is. So it spins. You can pause, of course, the simulation and then use the step button right here to move one frame forward and clearly see the cube's Y rotation changing. You should see that the 3D bounding box visualization does not update as you step through frames, but this does not affect the output that we want. So we can now rotate the cube, but we also want to move it around the table. However, not all positions on the table are valid, so we need to be within the robot arm's reach. We will use a predefined custom randomizer to do this. So I will go back to the scene, pause it, go back to the scene. I will go to the simulation scenario right here. So click to play to stop the scenario, click to simulation scenario, and then go to add randomizer and type here robot arm object position randomizer. Here we are. And now we will need some specific things. For example, set mean robot reachability to 0.2. Set max robot reachability to 0.4. On the plane field, click on the circular button to the right side and start typing object placement plane. And then again here to the robot base field, drag and drop the base of the robot from hierarchy tab right here. So click here, world base link, the base. So this is what we will drag and drop, and take the base, drag it and drop it right here. So now we need to add the corresponding randomizer tag to the cube. So select the cube object, and in the inspector tab, click on the add component, start typing robot arm object position randomizer right here, and this robot arm object position randomizer tag should be reachable. So click right here. Now, if you press the play button, you should see the cube and the goal objects moving around the robot with the cube rotating in each frame. So if you click the next step button, you will see that the cube and the goal objects are moving around the robot with the cube rotating on each frame. Now we will add another randomizer to introduce some variation into the scene's lighting. So we will click again to the play button to stop. Okay, that now stopped. So select now the simulation scenario, game object, and in the inspector tab on the pose estimation scenario right here, click on add randomizer. So we will click this one and start typing light randomizer. For the range parameter of light intensity, here we are, light intensity parameter, set mean to 0.9 and max to 1.1 as it is. Range parameter of rotation X, min 40 and max 80 as it is. And all the other values should be exactly as they are right here. So the last thing that we have to do is to add this randomizer tag to the light. So select the directional light game object and in the inspector tab, click on the add component button. Start typing light randomizer tag right here. So this light randomizer tag script is found, and then we could click the play button, and you will see that the color, the direction, and the intensity of the lighting now change with each frame right here. Again, you can pause and click step by step to run this script. Click the play button so that you will stop playing this scenario. What we just did is actually you learned how to equip the camera for the data collection, how to set up labeling and label configurations, and how to create your own randomizer and add custom randomizers. Now we will see how we can collect a large dataset of RGB images of the scene and the corresponding pose of the cube. We will then use this data to train a machine learning model to predict the cube's position and rotation from images taken by our camera. And finally, be ready to use the trained model for our pick and place task in the next steps.